So I had one more example from 5.1 that I wanted to kind of work through. I'll take some questions from you guys from the homework sets, and then we'll start 5.2. Cool? Okay. All right, so this example says, suppose the odometer on our car is broken, and we want to estimate the distance driven over a 30-second time interval. We take speedometer readings every 5 seconds and record them in the following table. So the first thing I notice is that we have a units issue. The times we measured in seconds and the velocities we measured in miles per hour. So we have to do some unit conversion to make that stuff match up before we start doing any kind of calculation here. What do you guys think? You want to turn those seconds into hours? I don't. Think about how obnoxiously small those decimals are going to be. Well, here's what I'm going to do, is I'm going to turn this into like feet per second. So like 17 miles per 1 hour. Yeah, I divide by the 3,600 to turn it into seconds, but then I multiply it by 5,280 feet. So it's going to be still pretty close to the number it was before. It won't be bonkers. That feels a little less obnoxious to me than dealing with like super tiny decimals. Wouldn't be wrong to do it the other way, but like, I don't know, feels unnecessary. So we'll call that 25. Since we're making an estimate already, I'm just going to round these to a whole number. Everybody cool with that? So I'll call that 31. It's probably a clever way for me to do this where I don't have to do it over and over again.
Oh my God.
35. I bet if I put this into a list, I could multiply the entire list by that conversion factor. But at this point, I'm kind of pot committed. I'm halfway through. So call that 43. Call the next one 32. Or I'm sorry, 47. And then call that 45. And we'll call that last one 41. Everybody's okay with that? So if I think about this as a function where this is time in seconds, 5, 10, 15, 20, 25, 30, 5, 10, 15, 20, 25, 30. Good, okay. And then this is in like feet per second. So say 10, 20, 30, 40, 50. So if I plot this, I'm kind of looking at something like this, right? Everybody agree? So if I think about this then as an area, if one dimension is in feet per second and the other dimension is in seconds, when I multiply those two dimensions, what am I going to get back out of here? Feet, a distance, exactly. So the area under this curve is going to represent the distance traveled by the vehicle. Everybody feel okay with that? Okay. So to do this, we're going to have to approximate it because we don't have a specific function for the curve. We're going to approximate it with rectangles because all we're given are specific point values. So let's do, we'll do right rectangles first. And then we'll also do, use that color. We'll do left rectangles after. Since one's going to be kind of an overestimate, the one will be kind of a little bit of an underestimate. If we average those two estimates together, we'll probably get the most accurate answer we can out of this data set. So I think I'm going to do both. It doesn't really give us instructions as to what it wants us to do with this, but I'm going to just choose to do both.
So sometimes it would say, like...
It might just say use the right-hand rule, or use the left-hand rule, or use the midpoint rule, or whatever. Like, it'll probably be specific if it wants you to do something specifically.
But
if not, well, if I could, I would use midpoints, which is probably is probably pretty equivalent to what I'm doing, but I can do it with one set of calculations instead of two. But I don't have data to do that, right? It would just be a guess as to what I think the value is in between there. Okay. So my delta x is just 5 seconds, right? That's the amount of distance in between each of my, or the base of each of my rectangles. Everybody agree with that? We're doing this from 0 to 30. So my A naught is A, or 0. My x1 is A plus 1 delta x, or 5. My x2 is A plus 2 delta x's, or 10. And I can just kind of keep going. Everybody's okay with that? So my rectangles here are going to be like 5 times, so if we're doing right hands, I'll have 31 plus 5 times 35 plus 5 times 43 plus 5 times 47 plus 5 times 45 plus 5 times 41. If I do my right hand rules, I'm going to be starting with 5 times 25, and then I'll have everything else will be the same except for the last one I'm not going to do. God bless you. You're welcome. Is that okay? All right. Let's do this thing then. Oops. That was supposed to be a 47. So 1210. And then the only difference between R and L is R has a 5 times 41, and in L that would be a 5 times 25. So I'm just going to change that one value. So I get 1130. The other one was 1210. And then we'll just kind of take our average then. And say that our distance traveled was approximately 1170. As a reasonable estimate. Is everybody okay with what we did there? Okay. You guys worked on some homework for me. Is there questions about any of that? Luke?
Do you mind taking a look at number 19?
Sure. Oops. Get on the right page first. So here it says, use definition 2 to find an expression for the area under the graph of f as a limit, and then don't evaluate the limit. Well, let's go remind ourselves what definition 2 said. So I'll just drop that in here for us. Okay. So definition 2 was just that formula for finding the area under the curve. So that's fine. It's a pretty ugly looking f of x though. Let me think on that, see if there's a clever way to do this so I'm not fighting with that the whole way through. All right, let's start here. So my A is 1, my B is 2. So my delta x would be like 3 minus 1 divided by n, or 2 over n. X naught is A, which would be 1. X1 would be A plus 1 delta x. So that would be 1 plus 2 over n. X2 would be A plus 2 delta x's, so 1 plus 4 over n. And I see in general xi would be then like 1 plus 2i over n.
Where does that xi come from?
Well, I'm just saying like in general, the pattern that's going on here, right? We're just taking whatever this is, multiplying it by delta x and adding to a.
Yeah.
So I'm just kind of like generalizing that because I think what I'm going to end up wanting to do is I'm going to probably try to use a summation here to make it like less obnoxious than writing out this with stuff plugged in every time. So it's just me getting out of having to write that kooky fraction like a bunch of times with the dot, dot, dot in there. I'm going to try to use the summation symbol to get away with not having to write that fraction over and over and over again. That's why I'm interested in figuring out what the ith x looks like. Does that feel okay? All right. So I know my area is the limit as n approaches infinity of, and then I'm going to have f of 1 plus 2n times 2 over n plus f of 1 plus 4n times 2 over n plus dot, 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 and then I'll have f of 1 plus 2n over n times 2 over n. That's like my, what I got there. I noticed that I can factor out a 2 over n from each term. So I can do that. And now I'm going to write this using a summation. And now I'm going to plug this in to my f of x. Now that I have just one f in there, I don't have to write like a trillion fractions. Not that it would have been wrong to do that, but it just would have been like obnoxious, like overly obnoxious to have to do that over and over again. Let's see, we have 2x over x squared plus 1. Okay. So we have 2 times, and my x is 1 plus 2i over n divided by x squared, so 1 plus 2i over n squared plus 1. And it says do not evaluate the limit, so I think that's probably where I want to stop. Yep.
So the third line below the area equation.
So you're talking about this guy?
Yeah.
Mm-hmm.
So at the very end, where it's f of 1 plus 2n over n,
Mm-hmm.
that 1 plus 2n over n comes from the algebra 2 concept that we looked at last class.
Well, it's really just it. Okay, so this is a plus 1 delta x. That's our x1. x2 is a plus 2 delta x's. So xn is going to be a plus n delta x's. And delta x was 2 over n. And notice that this simplifies down to 3, which if I'm doing a right-hand rule, should be the end point of my interval I'm summing over, which is indeed what I'm seeing there. So that's good. That tells me that I think everything looks good.
And then, do you mind explaining the sigma notation one more time?
Mm-hmm. Sure. So the I tells me like the index variable. So like this is the thing that is changing in each term of my sum. My sum is going to start when I is 1 and going to end when I is n. So this is like starting at x1, ending at xn. And then what's changing is the thing that I'm plugging into the f. So I wanted to use my expression for xi that I created earlier. So that's just what went in there. Does that feel okay?
Yeah.
Jack.
Sorry, so what is xi?
This is like the ith. So like we have the first x, the second x, the third x. This is like the ith x. And it ends at like the nth x.
So that's just some x between 1 and n.
Including 1 and n, yeah. It could represent any x between 1 and n.
Okay.
Including those endpoints. Yep. It's just like a general way of writing what those coordinates are that I'm going to be plugging in.
Oh, it's just okay. Yeah,
Right. It's always going to be 1 plus 2 over n times some integer.
Yeah.
Right.
Yeah.
1, 2, 3, 4, 10, whatever.
And you're showing that next thing. You're plugging it in. Okay.
Exactly.
Okay.
Yep.
So that's just the general like template.
Yes.
Okay.
Yes. Exactly.
Oh, okay.
That's exactly what it is.
Okay.
Yep.
Yeah, that makes sense. Thank you.
Sure. Luke, you happy?
Yeah, that's all good.
So again, mathematically, really light. It's just me getting comfortable using these formulas and like converting from a sum into a summation. And you don't even really need to do the summation. I chose to do that because if I didn't, each one of these would have to be like that annoying looking fraction. It just felt like it was going to be a lot of writing that I didn't want to have to do, which wouldn't be wrong if you did it that way. It's not wrong. They're equivalent expressions. They mean exactly the same things. The directions don't require summation. I just elected to do it because it was less writing. But you could have, instead of, you could have just plugged in these quantities in for your f of x at that point and been done. That would have been okay. Not as pretty as the way I wrote it, but it's correct. So take that for whatever it's worth. What else do you guys want to talk about?
What is the answer to 24?
Let me look here real quick. Oh, okay. You should have gotten 1/4 for part B. Yeah, nice work if that's the case. Part A was just like the formula using definition 2 again. That's rad if you got 1/4 to come out of that. That's great. Anybody else? Okay. We're going to continue here. Talking about these sums. So this process that we developed in section 1 is going to be the foundation for what we're going to do here in section 2. So we're going to start with the definition. So we say that if f is just some function on the interval, the closed interval from a to b, and we divide that interval into n subintervals, whose width is delta x, that's b minus a divided by n, and we let the x values equal, or just be the endpoints of those subintervals. So like x0 is a, x1, x2, xn is b. So x1 would be like a plus delta x, x2 would be a plus 2 delta x, x3 would be a plus 3 delta x. Everybody's okay with that? And then we pick some x value inside of those subintervals. So the subinterval from x0 to x1, pick some x in there. From x1 to x2, pick some x in there. x2 to x3, pick some x in there. Doesn't have to be an endpoint, doesn't have to be the midpoint, can be any point, doesn't have to be chosen even systematically. Any point will do.
So the asterisk.
That's what the asterisk means. Yep. We call those the sample points. And we say that xi star is the sample point from the ith subinterval, that being from xi minus 1 to xi. We define the definite integral from a to b. So this is the symbol for the definite integral. And it's this. What does that look like? That was definition 2 from last chapter, except we've replaced xi with xi star. So rather than requiring you to use an endpoint, any point from the interval is fine. Now it says, provided this limit exists and gives the same value for all possible choices of sample points, if that limit does exist, we say that f is integrable on that interval a to b. If that limit doesn't exist, then f is not integrable on this. So a little bit of notation here before we go and do an example. So this symbol kind of looks like a stretched out S. Why do you suppose we chose the letter S? Because it's a sum. It's just representing a sum. Okay? We call that stretched out S symbol the integral sign. Inside of our integral, the f of x we call the integrand. The a and the b are our limits of integration, where the a is the lower limit and the b is the upper limit. It's convenient that the lower one is on bottom and the upper is on top. And the dx part, that's kind of like the equivalent to our delta x. Grab that. It just indicates the independent variable. So in this case, we're integrating with respect to x. And the process of actually calculating the value here is called integration. So again, this thing is an integral. That piece is the integrand, and calculating what that sum is equal to, that process is called integration. Everybody's okay? Just a little bit of vocab. Okay. The definite integral is a number. That number does not depend on x. So if we just do a variable substitution, these all have the same value, right? The integral from a to b of f of x dx, it's the same thing as the integral from a to b of f of t dt, which is the same as the integral from a to b of f of r dr. It doesn't really matter. It's the same quantity. This sum that we looked at from last time has a special name. It's called the Riemann sum, or a Riemann sum, named after the German mathematician Bernhard Riemann, who I think was like a doctoral, like a PhD student for Carl Gauss, was like the most prominent mathematician of, like the 1700s. But Riemann himself is hugely, hugely influential in a large variety of mathematical areas. Still super, super important. So if we look to just kind of visualize what's going on, the picture here on the left is what a Riemann sum is, where you're adding up these rectangles. And the figure on the right where you're looking at the area underneath the curve, that's the definite integral. We know from the last section that as the width of those rectangles becomes infinitely small, the sum of those rectangles is going to equal the area under the curve, right? So that's all we've done, is we've connected this idea of adding up rectangles, and we formalized it into a new calculus operation called the integral, or the definite integral, I should say. So one thing we have to be careful about, if I look at the previous picture, the function has only positive values. It's always above the x-axis. But that needn't be the case, right? So if we have parts of our graph that go above the x-axis and below the x-axis, the parts that are below we're going to have to treat as like negative areas, which is not a big deal. That seems pretty intuitive. Although like a negative area is a purely like abstract concept. But all we're really doing here is just like taking the positive parts, adding them together, and subtracting off the negative area, right? Which seems, okay, sure, I can do that. And you don't really need to even think that hard about it, because when we calculate the areas of these rectangles, what are the heights going to be? Going to be negative values, because those are based on the value of the function at some point on the interval, which is a negative value because it's below the x-axis. So it's not even like you have to really think about remembering to subtract anything. We're just accounting for, yeah, this is an area as a negative number. So what? We know what we mean. Everybody's okay with that? Okay. So we have defined this definite integral for an integrable function, but not all functions are integrable. The following theorem shows that the most commonly occurring functions are in fact integrable. This theorem would be proved in more advanced courses. So it says if f is continuous on the closed interval from a to b, or if f has only a finite number of jump discontinuities, then f is integrable on the closed interval ab. That is, the integral from a to b of f of x dx exists.
Do we know like a common function that is not integrable? Like, is
Nope.
there an example? Oh, so it's
You want to see an example of one that is not integrable? Sure. So I need to come up with a function that has an infinite number of jump discontinuities. So again, remember what a jump discontinuity is. It's something like this. So here's what I'm going to do. Yep. So we'll have the function is equal to 0 if f is a rational, or if x is a rational number, and the function is equal to 1 if it's an irrational number. So in between any two values on any closed interval, there's an infinite number of each, rational numbers and irrational numbers. Ooh, if the endpoints are rational numbers, I know that there's an infinite number of both. If they're both irrational numbers, I'm not sure I can say there's an infinite number of rationals in between there. That I'm not positive of. But if they're rational, if the endpoints are rational, I know there's an infinite number of rationals in there also. So you'd have infinite jump discontinuities there.
So you couldn't even go about differentiating that.
Yeah.
Because it would just be, just like area to
Tegan, for you. Yeah, so it's to construct something that for us that's not integrable, you're going to really have to rely on some like foundational piece, like where it's just going to be a piecewise where things are rational or irrational, or like something like that. So it's gonna feel very artificial and very fishy. It's like I don't even know what I would do with this. That's because it's not integrable. All right. So if f is integrable on an interval ab, then the then in the limit in definition 2 exists and gives the same value no matter how we choose those sample points x star. To simplify the calculation of the integral, we often take the sample points to be right endpoints. So since it doesn't matter how we choose our sample points, let's just choose them the same way every time. And let's just choose a right endpoint. Since it doesn't matter, we're just going to pick one. We're going to pick the right endpoint. So if that happens, then our definition just simplifies down to this, which is exactly what we did in the previous example. Which is awesome, right? Nice. I'm very happy. Or not the previous, but the previous question, the one Luke asked about, right? Is exactly what we did. Okay. So, first example, we're going to rewrite this Riemann sum as an integral. So we'll start by drawing our integration symbol. Since we're integrating on the interval from 0 to pi, that's my lower bound and my upper bound. The integrand is the function that we're summing. Notice the only thing I did there is I just dropped the subscripts. Instead of xi's, I just have x's. And then instead of delta x, I write dx. And I'm done. All we did is change the symbol from a Riemann sum to an integral. That's it. That's all we're doing. They mean the same thing.
What is the smallest sub thing that is?
It's an I.
Okay, I thought
Yeah.
so.
Yep. Yeah. In fact, it doesn't even really matter what the variable name is. It just needs to match the variable on the sum. So if you used i's or z's or a's or whatever, I wouldn't do x's because we've already used x in there, but I wouldn't use n because that's the upper limit. But any other letters I would say are fair game as long as they match. J's, K's, H's. Taylor, did I see your hand?
I had the
Same question. Cool. And that was very easy, right? It's just a question of like understanding the notation. Okay. So if we're going to calculate one of these integrals, it's going to come down to computing this sum or computing that limit, which means we're going to have to find a formula for the sum so we can use our limit tricks to evaluate that. In order to do that, we're going to give you some summation formulas. So these are things that conceivably would have been covered in or talked about briefly in your Algebra 2 class when you talked about sequences and series. So the first three are limit formulas for that you'll use to like piece together a polynomial. And the second four are summation formulas that allow you to manipulate a more complicated sum so you can turn it into like 5, 6, and 7. Let's do an example here where we use this to actually evaluate one of these summations. Sound good? And to be honest with you guys, it's not even really super duper duper important that we're memorize those summation formulas because we're not going to use them for very long. We're going to get away from using the limit of these sums pretty quickly to do these integrals. So this is just like a stepping stone along the way. So don't freak out about going and trying to memorize these things all right away. Okay? So just like real talk here, right? All right. It says to evaluate the Riemann sum for f of x equals x cubed minus 6x, taking the sample points to be right endpoints, and a to be 0, b to be 3, and n to be 6. So my delta x is 1/2. So I'm going to have 6 right-hand endpoints. So again, how did I do this? It was a plus delta x, and then a plus 2 delta x, a plus 3 delta x, etc. I just did it quickly in my head because the numbers were all very round and even, and it was very easy to calculate them quickly. Okay. So we're doing the sum from I equals 1 to 6 of f of xi delta x. Or really, what is this? It's 1/2 times 1/2 cubed minus 6 times 1/2 plus 1/2 times 1 cubed minus 6 times 1 plus 1/2 times 3.5 cubed minus 6 times 3.5 plus 1/2 times 2 cubed minus 6 times 2 plus 1/2 of 2.5 cubed minus 6 times 2.5 plus 1/2 times 3 cubed minus 6 times 3.
How important that we write all of that out?
Not, to be honest with you, like I'm going to do this all in the calculator here. So I'm going to type in the function into y1. So I'm going to do 1/2 times vars, y vars function y1. And then I'm going to do 0 plus 1 times delta x. Press enter. And then we're going to add that to, I'm going to have to do it that way. So I got to insert this in and do ands plus, and then I'm going to update this to be 2 times, and then I'll do it again and update that to be 3 times, and then update that again to be 4 times, update that again to be 5 times, and then update that one more time to be 6 times. So I get negative 3.9375. Any way you want to type that in, whether you type it all in one line or you did it the way that I did it, where I just was trying to minimize my button pushing, is all I was doing there. I wasn't doing anything sneaky. I was just typing in that one term at a time, so that instead of having to do it all in one line and potentially making a mess out of something, I'm just going to do it once right, and then just update what I had before, so it just keeps accumulating. So that's like part A. So part B says then to evaluate the integral, so I'm going to start by using my definition for the definite integral. Okay. So far, so good. So delta x in this case is going to be 3 minus 0 over n, or 3 over n. My xi is going to be 0, well, let's write it, a plus I times delta x, or 0 plus 3i over n, or just 3i over n. So far, so good. Okay, so I'm going to go ahead and plug that stuff in. So the 3 over n doesn't have an I in it. So I can treat that like a constant and pull it out of the summation, but it still has to be inside the limit. And then I'm going to plug 3i over n into my f of x.
Why do you need to keep the 3 inside the limit? I thought with like a limit law that could be outside.
The what?
Or why does the 3 over n need to be inside the limit still?
Because it has an n in it. So I could pull the 3 and write 3 out front and 1 over n. That's fine.
Okay.
But the n is the same variable that we're sending to infinity. So that part needs to be inside the limit. And I'm just going to leave the 3 in there because if I can't take the whole thing out, I'm just going to leave it in there because it's not really causing me any hassle.
Is that because like that n is actually a constant? If it was a constant, you could...
Correct. If it was like a k where n goes to infinity, suck it out front. Absolutely.
Okay.
Yep, these are good questions. Still doing okay? All right. So I'm going to now go ahead and simplify. Guess I've lost my summation into limits there. It's going to be 27n or 27i cubed over n cubed minus 18i over n. So what I'm going to do now is the only thing that has an I in it are these, right? So I'm going to use my summation rules so I can distribute my sum across the subtraction. And then I can take anything that doesn't have the I in it out front of the sums. So I'm going to use those two rules as my next step. I'm going to use a million lines here on this. That's okay, though. Okay. Now, this piece and this piece, we have formulas for. Those are numbers 5 and 7. So I'm going to go ahead and drop those in. That's going to eliminate the i's and the summation symbols. So the only variable I'm going to have left in here is an n. So far, so good. Okay. What I'm going to do now is I'm going to distribute the 3 over n through. And then I'm going to distribute the limit through as well. And I'm going to do some other simplifying as well. So when I square this, I'm going to have n to the 4th plus 2n squared. Fourth, yeah. And then it's going to n squared, okay. Ugh, come on, Mr. Kulik. N squared plus n times n squared plus n to the 4th. Oh, this would be n cubed. There we go. Plus n over 4 minus 54 n squared times n squared plus n over 2. Oops. And I guess at the same time, let's distribute the limit through. And we're just going to shortcut the limits because we're almost out of time here. I noticed that both of these are indeterminate forms because it's n to the 4th as the leading power over n to the 4th. I know that that's just going to simplify down to leading coefficient over leading coefficient. Similarly on the other one. So if we make a common denominator here, we end up with negative 27 over 4. Oh, Elvis? Yeah, so if we go back and look at formula 7, the sum of I cubed is that thing squared. So that's where the why the cubed went away and the squared came in. It's just the formula.
Why did you put the common denominator? Or the common denominator?
Well, I had to subtract the two fractions. I just had 81 over 4 minus 54 over 2, so I just made a common denominator. And there's my answer. What a nightmare, right?
That's the final answer.
That's our final answer.
But what happened to the limits?
Uh,
Yeah, that's fine.
right. So when I did, so right here, this is an indeterminate limit, right? Because we have, well, if we plug in infinities, I'm gonna have infinity over infinity, right? Because they're both the same degree polynomial, degree 4 over degree 4. I would just L'Hopital rule that 4 times. And when I reduce my fraction, I'm going to end up with just the leading coefficient over the leading coefficient.
So even though it's a polynomial, what if it was like, what if it was 81 over n?
Well, then you'd have an infinite
Oh, so you would.
there, so your integral would, the area under the curve would be infinite. That can happen. You can definitely have a definite integral that has an infinite area underneath it.
So,
What would that look like?
um,
Like if you have, like you're coming up to a vertical asymptote where it's going up and up and up, but never actually getting there. Something like that could have an infinite area underneath it, which is cool. Not really, Mr. Kulik. Does that feel okay?
Most of the time, they're going to be the same.
Here's the thing. Yes. And here's the thing. This process we just did, it's going to die a hard death in about one more section.
And it's going to be easier.
oh, is this like differential
Yeah.
where there's going to be like a shortcut?
Yeah. Just like how we did and when we learned a derivative, we start by doing the, like evaluating the difference quotient with the limit,
So it's
and
like
it
a-
stunk.
Yes.
And then like 2 sections later, we learned the differentiable or differentiation rules, and you're like, oh, this makes life so much easier. So that is coming here in a section or 2. I can't remember if it's, oh, one more section, it's coming.
Okay. I'm ready.
So we're going to get rid of this, jettison this sum of rectangles thing in favor of something else.
Will it still be something? Not that I would discount it, but it's something that's going to be on the exam and on our tests. The Ryman or that guy. And
Riemann sums?
Fun rectangles.
Yeah, these are things that'll pop up, and certainly if you don't have a defined function, if what you have is a table of values,
Yeah.
then you have to use these techniques.
Okay.
And even in fact, like in statistics in particular, this is a super important topic because not every function is integrable, and in particular, doing this kind of technique to approximate a probability density function like the PDF, the area under the curve, doing this or simulating that probability using like a method called like MCMC, Markov Chain Monte Carlo, where you're simulating the function and calculating the area under the curve, is like super duper relevant. But for us right now and what you're doing, what we just did there, that colossal mess pain in the butt, stands alone in this section. Like that dies one more section and we stop worrying about this. Unless you're given like a table of values, but then it's a purely numeric problem where the summation formulas don't matter,
Okay.
right? We're just,
Table of values, you just use the Riemann.
yeah, you're just doing a Riemann sum, but it's like a finite number of things. You can't do it infinite. You don't need a summation formula to do it. Forget it, right? Anise.
I know that.
Sure. All right. What do we have left? We have a lot of time still. Okay. I'm gonna stop right here, and we're gonna change gears for a moment. We'll finish the rest of this section next time. I still have kind of a lot of stuff to do, and this feels like a nice stopping point to change up. And I had mentioned that we wanted to talk about some of the exam questions from first semester. Let's do that for the next 15 minutes or whatever and call this a day. This feels like a good stopping point. Everybody's brain feels probably appropriately cooked on this new topic. Victoria?
From what we just learned from 5.2, what part of the homework is that?
What?
Is that just like 1.2, 1.5?
let's look here real quick. You could certainly do anything up to probably like 25 or 20 or so. No, I mean you could keep going past. I mean, like to a, it's hard because it's not like sorted like that, the homework, right? So like if you're just asking to evaluate an integral, like this example is what you're going to do. It may get a little sneakier than that, but like the tricks are just what we're going to be seeing after this is mostly just tricks. So like I would just do the stuff that like, okay, I think I know what I'm doing. And if you don't, just skip it and like we'll do some more lecture and you can circle back to it or ask questions. It's, you know, it's not been a big deal. Mr. Gulick tries to not make any of this a big deal. So let's take a few minutes and just talk about from the exam. This is 1 through 6. These are just limit problems. And this I think is kind of nice because we're doing a lot of limit stuff right now when we're evaluating these definite integrals. So this fits, I think, pretty nicely. So if I looked at number 1, if I plug this in, I get an indefinite. I get 0 over 0. So you have 2 choices here. One choice could be, well, I would say actually 3 choices. You could L'Hopital this. I wouldn't. You could multiply the top and bottom. Oh, no, you can't. Yeah. So the other way that I would do this is just factor. And this is what the majority of you guys did on the exam that did this problem. And those guys reduce out, and then you can just plug in and you're done. In fact, I don't think you can L'Hopital this because this is an infinite. This one looks really nasty, but it's just a direct substitution one. So when I plug this in, if I plug 0 in here, all those guys become 0 except for this part. So I have 1 times sine 0, which is 0. So just 1 times 0 is 0. 3, I think, was probably the most difficult one on this first page. Because this is indeterminate and you got to use L'Hopital on it, but you have to be really careful on how you kind of construct your quotient to do the L'Hopital with. So let's do this one carefully instead of just kind of Mr. Kulik hand waves at it. So I'm going to start by doing this. Again, I recognize this is like infinity minus infinity. That's indeterminate form. Somehow I have to turn this into a fraction. What I'm going to do here is I'm going to factor out a 1 over x. Okay, with that. Then I'm going to remember that the limit of a product is the product of the limits. And then in here, I remember that I can distribute a limit. And this piece, I'm going to L'Hopital. The other pieces I can evaluate just by direct substitution, but that piece is going to get L'Hopitaled. So the limit as 0, x approaches 0 of 1 over x is infinity. The limit as x approaches 0 of 1 is just 1. We L'Hopital this last piece, and I have 1 over x over negative 1 over x squared. When I simplify that, it turns into just negative x. So when I simplify, or now I can direct substitute. So I have infinity times 1 minus 0. Sure. Which is infinity. I think that was the hardest one on there because there were so many like little limit rules you had to use to kind of separate those limits up into parts before you could L'Hopital that one. I don't think anybody did it correctly. I think people figured out that by looking at their calculator it was going to be infinite. I don't think anybody did the algebra part correctly, which is good. I mean, that's something, right? Like you're doing calculus. You're looking at a graph and interpreting the limit. That is calculus. It's not following the directions, but you did calculus there, so I was happy with that.
Do you like notice when we do that, when we look at our calculator?
Absolutely.
And then we write like random numbers?
Oh yeah, I can totally tell. Yes.
Okay.
So again, this is another indeterminate form problem. So I'll write it as a fraction. This is nice because I can just use L'Hopital on this. I have infinity over infinity. So if I do one L'Hopital, I'm going to end up with, what's the derivative of the top? E to the x squared times the derivative of the inside, 2x, and the derivative of the denominator is, those can reduce. So when I direct substitute, I just get infinity. Everybody's okay with that? Okay. This one, again, infinity over infinity. Oh, no, actually, it's going to be 0 over 0 since it's negative infinities. Or, I'm sorry, infinity over 0. Anyway, it's still indeterminate. Whatever. How many L'Hopitals am I going to use on this? 3. So the numerator just is going to become that. So plug in infinity for this, and it should go to 0. This last one was the least amount of points earned on page 1. I think most people skipped it because when you look at this, or that they tried it, they had the wrong value for cotangent when they plugged in. This is going to be 1 to the infinity. Cotangent has an asymptote at 0, so it has an infinite at that end, or that side of 0. So this is 1 to the infinity. This is an indeterminate form. So the way you want to think about this is you want to take the natural log of both sides. That allows you to move the exponent to a coefficient. I remember that cotangent is 1 over tangent. So that allows me to write it as a fraction really easily. And now I'm going to do the limit as x approaches 0 of that. Still indeterminate, but now it's in a form where I can do L'Hopital on it. So this actually is fine. When I plug in 0, I get 3 on top. And what's secant of 0? 1, because cosine of 0 is also 1, and secant just the reciprocal. So that's 3, but that's not what I want, right? I need the limit of y. And what did I just calculate? The limit of the natural log of y. So I'll write it this way. And I know that's going to be then, since the limit of the natural log of y is 3, this is going to be e to the 3rd. Amanda,
Will we be getting our exams back for being
if you'd like to come and look at them, I'd be happy to show you, let you look at your exam at, I don't know, commute time or something. Be happy to do that. I'm not going to pass them back because, I don't know, we don't do that in general as a policy, as a school-wide policy. But I plan on just kind of like randomly filling some time here and there by going through exam questions, in particular stuff that not a lot of people got. So on this page would be like 3 and 6 were the ones that really were kind of the poor results. I think did I mention this last time that I went and showed you this graph? This was like the percentage of points earned for each question on the exam. So keep in mind, like, again, 6, not a lot of points earned because not a lot of people attempted it. Like less than 10% of the total points earned for 6 were earned. Most people skipped it. 3 was also pretty low because, again, it was pretty tough. More points earned there because at least people looked at the graph and were able to figure it out. It would have been tough to look at the graph and figure out e to the 3rd, though, for 6. I don't know that would have been reasonable. But in general, the limit stuff, like the first 2 questions were quite good, right? Most people saw what to do with those. And even 4 and 5 were not bad. Like, people recognized L'Hopital stuff needed to do there. The people that did them right. So not bad, but it definitely, like, my favorite pattern was I noticed that once you got to the multiple choice questions, like as you started the question, like the points earned just kind of goes down as you go through the parts, which is not surprising. The beginning parts were very much like draw a picture, like show that this thing is true, where I've already kind of given you the answer, like, you know, like, here's the formula, just do the derivative for it, kind of like, but we'll finish 5.2 tomorrow, and then, or not tomorrow, you know, the next time we meet. And then 5.3, we're going to greatly streamline this process we've been working on by connecting the antiderivatives that we were doing last semester with the definite integral. So instead of doing summations, we're going to just be doing antiderivatives, which is a massive improvement because those were much, much easier